Thanks for having me. Yeah, I've done a lot of work on catalyst and jump processes, but I'm going to tell you about something different today. This is a little package that was designed for work I'm doing with the lab of Omer Dushek's group at Oxford, but it's worked out really well, and it's enabled them to do these SPR experiments and analyze them and get more information than they could in the past. The paper will hopefully go out next week, and the paper soon, so I thought the software soon, so I thought I'd tell you about it today. So what I'm going to talk about is a kind of approach that feeds into this package, and then the package ultimately allows you to try to estimate binding kinetics from what are called surface plasmon resonance assays, and I'll tell you very briefly what those are. The example I'm going to do for today as motivation is antibody-antigen binding, and the example that we'll actually show you data on, if I don't run out of time, is measuring binding kinetics of SARS-CoV-2 receptor binding domain, so that's our antigen, to patient-derived monoclonal antibodies. So just in case you're not familiar with this what I mean by all this, this is a structure of, in the middle there, a bivalent antibody. This is specifically the FD11A monoclonal antibody to the receptor binding domain. And then here you see it has two binding sites. That's why we call it bivalent, where these receptor binding domains can attach to it, come in and bind, and they can form a complex. And so the kind of goal of this project, or Omer's lab and our work with them, is to try to understand and predict antibody function. Specifically, what I'm going to tell you about today and what we're working towards is, can we understand how biophysical and kinetic parameters of this process might be able to help in predicting antibody neutralization? That is the ability of an antibody to bind antigens like COVID. And another goal is, can we enable high throughput screens where they can compare a whole lot of antibodies against a single antigen to try to assess which ones might be best at neutralizing that antigen in some sense. So Omer's lab uses what are called surface plasmon resonance assays to try to estimate binding kinetics. I'm going to tell you how the classical experiment works, and then kind of our new version or model in a minute. I don't really know the details of how SPR works myself, but basically you have a device with a sensor surface that can measure refractive index changes. You get out a single signal that's given to you in arbitrary response units. And what's useful about this signal is it's directly proportional to changes in mass at the surface. So basically, as things bind to the surface of this device, you get a measurement of the change in mass that's going on. So kind of a classical monovalent SPR assay that people have been doing for many years would be the following kind of setup. So here I'd have my antibodies, and then in a solution above them, I would flow over the antigen, like the receptor binding domain. And then each arm of the antibody can have an antigen bind to it, and you would just assume there's some rate it binds and some rate it unbinds. In actuality, this is a 3D problem, so these are kind of often in a 3D region at the surface. So it's not, I'm drawing it as 2D, but it's really 3D, which will matter a little bit more later. And then what one gets out of it is a set of curves that looks like this. So these are the response curves, and in this case, it's a response curve for 6 different concentrations of antigen that they flow over. So, of course, as the antigen concentration goes up, you get a larger response. And often they do these experiments so that to give more features to the curve for parameter estimation, where after a certain time, they wash out all the antigen from solution, and so all that can happen is the antigen unbinds, and you get these kind of decay curves. So you get this kind of two-phase type behavior. And the standard thing that one would then do is to fit an ODE model to, say, these 6 curves simultaneously to try to estimate those 2 parameters, okay? And this comes built into all SPR software as far as I'm aware, and it's kind of a standard thing. But there's some problems with that approach in a few different ways. So one is that it kind of misses some of the physics one might see when you think about an antibody binding to antigen on the surface of a virus, which is that a bivalent antibody will come in and bind, and then it has this free binding site or arm, and that can then itself bind to another antigen. But there's a constraint that, of course, this can't bind to an antigen that's way over here. It can only bind to an antigen that's sufficiently close. So there's kind of a physical distance over which binding can occur. And there's also no reason that once it's bound, this second binding step is really the exact same rate as the first. And this distance over which this can bind another antigen, for today's talk I'm going to call the reach, and it's going to be something that ends up being very important, and we try to estimate it in our models. Okay, some other issues with the kind of classical approach is that it requires you to attach the antibodies to the surface and flow over the antigen. That's a challenge if you want to do high throughput assays of comparing many antibodies to one antigen. You kind of like the flip of attach the antigen to the SPR surface, flow over antibodies, make a measurement, repeat with a different antibody. And finally, in many cases, the parameters, this K on and K off you get, don't predict neutralization super well in many cases. So it doesn't help you in all cases with trying to predict how well an antibody can neutralize an antigen. So this was kind of the motivation for developing a new model that's maybe a more detailed physical model of the process, a new assay approach, which has been used in other contexts but is new when coupled to this model, and then a simulation package to kind of let you do the parameter estimation, which is what I'm going to tell you about today. So the new approach we're going to work out is what's called a bivalent experiment and model. And so basically we flip the experiment. Now we put the antigen, like the receptor binding domain, on the SPR device, and we flow over our antibodies. And now we have more information and a more detailed model. So we assume that there's the same on and off rate that an antibody can bind to an antigen and have one arm bound. So these should physically, we would think, be the same as what you'd measure in the monovalent. But then once it's bound, we assume that for all antigen that are close enough within reach, which I call epsilon, there's some rate K on B that it can bind those. So we've got two more physical parameters, this distance that an antibody that's bound one arm can bind to another nearby antigen, and then the rate of that binding step. And so to take into account this kind of spatial effect, and that you may only have very few binding partners, which could add stochasticity to the system, we developed a particle spatial stochastic jump process model for this whole thing. And I'm not going to go into the math details, but I'm happy to talk about it afterwards. But basically, the model we put down in 3D, because this is really 3D, a whole bunch of antigen particles. And then we simulate with jump processes the binding and unbinding of antibodies and the binding of the singly bound antibodies to nearby antigen with some probability per time. In the new model, we assume that what the SPR device measures is a signal that's proportional to the average number or amount of antibodies that are bound to antigen at the surface. And then we can simulate this using standard jump process simulation algorithms like the Gillespie method or the stochastic simulation algorithm. But there's one little challenge with this, which any of you that simulate jump processes know, which is that simulating jump processes can get computationally expensive. You have to, since it's a stochastic simulation, you have to run a number of simulations. You need to average them if you want to calculate an average response to fit against data. And in practice, that slows down the workflow for an experimentalist who gets their SPR data and wants to immediately say, what are the parameters that I've now, that matches up with this data? So to try to make the whole process faster for them, we decided to explore and use a surrogate approach. So basically, it's kind of embarrassing to give this, but we did the dumbest, simplest thing you could think of, which is we just built essentially a piecewise linear interpolation table. So that is, we took our 4 physical parameters, and we essentially took a big swath of parameter space that we thought they would generally lie in for the types of experiments we were looking at. We tabulated over that portion of parameter space with some resolution simulated response curves from this particle model. And then when someone runs an SPR experiment, we just do linear interpolation when fitting to evaluate candidate curves for parameter values that we didn't actually calculate it for. So here we have some piecewise linear surrogate function that essentially just does the interpolation over our table for a given set of parameters at a given time. And that's what we can, and then there's a scaling constant that we have to fit to, because all we know is the response units and that they're proportional to the amount of antibodies bound at the surface, but not directly equal to. So there's 5 parameters that you end up having to fit over. And then essentially we optimize trying to minimize the difference between this and the SPR data. So SPRFitting.jl is the package we put together to carry out this process. And it basically lets you do the forward model particle simulations of the stochastic model. It also does the surrogate construction and then evaluation. And for the evaluation, it's very simple because it's just piecewise linear interpolation. But we use the interpolations.jl package, We also have some tooling to batch it on clusters so you can split up and build the surrogate in parallel independently. Generally, we can build them in 500 to 2,000 CPU hours, one surrogate that they can then use for weeks, typically with a set of SPR experiments. Once you've got your surrogate, then you take your SPR data that comes out of a given experiment and the surrogate, and you do parameter estimation. Here we just leverage optimization.jl, and in the current or initial version of the package, we just used XNES from Black Box Optimum. We found that worked very well. And then output from that is your biophysical bivalent model parameters. So the on and off rate that the monovalent model would give you, the second binding rate, and this distance that an antibody bound to an antigen can bind and interact with another antigen. And one of the things I'm not going to have time to show you, but that's kind of cool, is that when we correlate these with neutralization, actually, this ends up being the best correlate we found when we compare to experimental assays on neutralization. And then, of course, with the parameters in the forward model, you can go and run forward simulations and then predict measures of neutralization. The one that I'll talk about today and show you in my last minute or two is called IC50. If you don't know what that is, probably most of you don't worry about it. I'm happy to explain it afterwards. But basically, it's a way that you can try to assess neutralization, at least in a chemical setting. So let me just show you two outputs. There's a lot of stuff. The paper, like I said, should go up next week. But these are kind of just some kind of neutralization predictions. So here I'm showing you, I guess, 6 different antibodies to the receptor binding domain of COVID. And the ones I boxed are 3 that do very well at binding to it. And what you see are the experimental neutralization measurements, what our model predicts, and then what the classical model predicts. And so you see for all 3 of these, our model does really well compared to the classical model, and it's much closer to what's predicted from experiments. We don't do good on Regeneron. We don't know why we didn't do good on Regeneron. And then there's 2 where these antibodies actually can't block ACE2 binding, and there's a bit of a structural story, so they're not great at neutralizing, and we don't do good at predicting ones that don't neutralize well, it seems, or at least these ones. So there's kind of a structural story, but among certain classes where they seem to interact near the tip of the receptor binding domain, we actually do very good at predicting neutralization. So let me just end with kind of one last graph. So here's just a broader panel that my collaborators ran, where they looked at a panel of 25 different antibodies where the binding site is close to the ACE2 blocking site. And in this case, we see quite good agreement between what's predicted from the SPR fit and then the estimated parameters, and then the neutralization prediction out of the model using the estimated parameters compared to the actual what's measured experimentally. And so I think I'm about out of time, but let me just thank the people that have worked on this. So Omar's lab is a real expert in doing these kinds of assays. They've used them for a long time for problems with regards to T-cell receptor signaling and other types of immune signaling, and that's something we're working on with them too. Anna really did all the hard work with doing the data analysis and running the fitting and kind of a lot of the inferences from the results we found. Dan Wilson worked with me in developing the methodology, and then there's a large number of other people that have participated in this. And thank you all for coming to the talk.
Thank you, Samuel. We have time for a few questions.
Thank you for the nice talk. It's a neat little trick that you did there. I was wondering, is the data that you're comparing to spatial or
nope.
not?
SPR just gives you a measure for the amount of stuff bound across the surface.
So did you try simplifying back your spatial
model
back to multi-compartment ODEs or something?
Yeah, but we want to have the spatial reach in there because that we found was very important. So we've tried simpler spatial moment closure approximations, and they didn't work well. And some of that was because when you integrate them over space to get like the total response, you lose the spatial actual parameters out of them. It doesn't seem to actually be in there very well. So yes, we have tried simpler models for it, but capturing the spatial interaction distance was a key part of what we wanted to try to do. So, yeah.
I think we would have time for one more question. We need to start with a final talk for this session. No? Yeah.
Yeah, so you're estimating, I think, these four parameters, right? And you're using optimization.jl. Do you also have any sense of the confidence intervals around these parameters?
You mean like a statistical confidence interval around them?
Yeah, for instance.
No, I mean, so the main validation that we've done is by comparing to experimental data as best we can. And so we have a lot of that in the paper, and that looks pretty good in what we've, so well, I'm not on now. So the K on and the K off, you can estimate by monovalent, and we get good agreement with monovalent for those. So that's part of our validation we use for those two parameters. For the others, we don't have like any more systematic approaches that we've looked at. So beyond comparing to other experimental measures like molecular dynamics simulations, which we have done that, and that's in the paper, and there's very good agreement in the predictions there. So we kind of, I guess, assessed it by comparing to other experimental measures. That was the main thing we tried to look at. So.
Okay, thank you very much.
Yeah.